Welcome to The Explainer. Today, we're going to crack the code behind one of humanity's most perfect shapes, the circle. Now, it might look simple, but it's actually governed by this set of beautifully logical and interconnected rules.
So what if I told you that one single rule could basically explain the whole shebang? Well, that's pretty much what we're going to find out. We are about to uncover the hidden logic that governs every circle in the universe, all from a single starting point. Our journey starts with this one powerful idea that really acts like a master key. Seriously, once you understand this one theorem, it unlocks almost all the others.
Okay, so here it is. This one statement is the foundation, the bedrock for everything we're about to discover. It connects the very center of the circle to any point on its edge in this precise and predictable way. But, how do we actually know it's true?
Well, the proof is surprisingly elegant. All we have to do is draw this one extra line. That's it. It splits our main angle into two parts, and more importantly, it creates two special little triangles for us to work with.
And here's the key. The lines from the center to the edge, they're all radii, which means they're all the exact same length, and that forces these triangles to be isosceles. And what do we know about isosceles triangles? Their base angles are always equal.
So here's where it all clicks. There's this fundamental rule about triangles, and since we know those two base angles are equal, it means the external angle at the center is simply double the angle at the edge for each of our little triangles.
And just like that, it's proven. You just add the pieces back together and the relationship is undeniable. The total angle at the center is exactly double the angle at the circumference. So now that we have our master key, let's go see what puzzles we can unlock.
All right, now for the fun part. We can use our master key to rapidly unlock some of the circle's most famous secrets. We don't need any new proofs, just new ways to apply the rule we just learned.
So let's think about a new puzzle. Imagine you have two different points on the circumference, but they're both looking back at the very same arc. What does our rule tell us about the angles they create?
It's really that simple. Since both of those angles are subtended by the same arc, they must both be half of the exact same angle at the center. So, logically, they have to be equal to each other. Boom, another theorem unlocked.
Okay, but what if we stretch that arc all the way out so the chord becomes a diameter, creating a perfect semicircle? This is a classic special case, but you'll see our master key still holds up perfectly.
So, the arc is now half the circle, which means the angle at the center isn't really an angle anymore, it's just a straight line. And a straight line, of course, is 180 degrees. So if the angle at the center is 180, what must the angle at the circumference be?
Exactly half, 90 degrees. This means the angle in a semicircle is always, without fail, a perfect right angle. This is a beautiful and incredibly useful result that flows directly from our master key.
Okay, let's shift our focus. We've been looking at angles inside the circle. Now let's look at lines that interact with it from the outside, where that same elegance and predictability still applies.
First, a little vocabulary. A secant is a line that just slices right through a circle. But a tangent is more delicate. It just gently touches the circle at exactly one spot. It's really important to know the difference between a line that cuts and a line that just touches. And here is the absolute core rule for tangents. Wherever a tangent touches a circle, the radius that meets it at that exact point will always form a perfect 90-degree angle. That gives us another reliable right angle to work with, which is super useful. So this sets up a new puzzle. What if we have a single point outside the circle and we draw two lines from it that each just touch the circle? Are the lengths of those two tangent lines related at all? Well, we can solve this by connecting the dots back to the circle's center. So if we construct these two triangles, we can see they both have a right angle. They share the same hypotenuse, and one of their other sides is a radius, so we know those are equal. Because of all that, the triangles have to be identical, or congruent. And if the triangles are identical, the conclusion is unavoidable. The two tangent lines must be the exact same length.
So what have we discovered on this quick journey? Let's just step back and recap the elegant code we've managed to unlock.
We've seen how a few simple interconnected rules create this incredibly elegant and predictable system. It's not just a collection of random facts, right? It's a logical structure where each piece builds on the last, all starting from that one master key theorem.
And the real takeaway here is that this isn't just abstract math for a test. This is a fundamental blueprint for the world around us, and it's hiding in plain sight. These rules dictate how gears turn, how satellites orbit, how light is focused through a lens. So the question isn't just what these theorems are, it's where you're going to start to recognize their perfect logic in your own world.